This meter, no. Okay, hopefully it works now. Oh, so many people. Okay. Oh shit, I forgot. 可以去帮我，我想想看，办公室帮我拿麦克风，应该在桌上，就是这只。Okay. Let's get. Wait, sorry. Wait, why isn't this working? Let's see. Technical issue. Let me try. Why is this not? Let me see this thing, and it is even connected. Wait. Okay, maybe this one. Sorry for the technical issue. And now we should do something. It is broken. Okay, excuse me, let me try this. Maybe this will work. Okay, now we have something. Okay. One way or another, we can do what we want to do now. Okay. Yeah, so welcome to the quantum computation course. And well, we have a lot of people here. Anyway, so this course is about quantum computation, and that's the syllabus here for now. And we will talk a lot of things. So basically, I will teach you basic about quantum computation and quantum algorithm. And we assume that you don't have too much background, but I guess you need some mathematical background, so you need to know a bit about calculus, linear algebra, and calculus and linear algebra mostly. And if you know computer science, it will be a bit better. And but I assume you don't know physics. Okay, so the part about quantum mechanics I will teach you. And so this is our course textbook. This is a famous one. It's Nielsen and Chuang, and it's a bit annoying, but it's pretty detailed. So yeah.
Can I turn off the lights?
The first row, sure. Yeah, so someone can try to do that. Are you guys able to see this? Yeah. Yeah, you go ahead. Let's see. Now this one, right? You want to turn off that one, right? Wait. Now this one. You turn off the wrong one. 你刚才是想把这个配板的关掉啊？应该是比较好。你顺序帮忙弄掉。第一排的灯打开吧。Okay. Yeah. Oh. It is very low. Yeah, thanks. Yeah. Okay, sorry for the delay. And anyway, so this is quantum computation. And let me try to make this smaller. Okay. Yeah, and this is a textbook, and well, the lecture is going to follow mostly from the textbook, but I also have my lecture note, so you should be able to see this. And yeah, we will have our problem set also written out. And here are some references. Those are online lecture notes I found good, and yeah, you can read them. You have extra time. Although the syllabus will be posted on website. Yeah, and well, the teaching method is mostly lecture, and there will be homework and there will be test. Oh, also I forgot. So, but this year we are doing something extra, so we also have like a little bit of a programming part. So somewhere in the course you will be asked to try what's that called? You will try to do the IBM QC. IBMQ, there will be a there will be an assignment for you to write the program on this IBMQ simulator somewhere in the course. Okay. And yeah, so here are the things we are going to teach. So the style I'm going to teach you about basics, so about what are quantum state, what are quantum measurement, entanglement, etc. So we start with teaching about quantum mechanics, then we go to complexity theory a little bit, so teach a little bit of the basics about computer science. And so those are big things. Then the second half of the course will teach you about the two famous algorithms. So there is the short factoring algorithm, and there is the global search algorithm. And we probably don't have extra time because we are changing from 18 weeks to 16 weeks. But I have extra time. There are interesting things we can talk about. Okay. And here is all things are evaluated. So mostly it's on the test. It has 70% and the homework are 30%. And homework policy. So we will have weekly homeworks, and there will be all and due on every Thursday. Hopefully they don't take you too long. And turn-in actually, so turn-in I guess mostly is turn-in in class, but it's basically any way you can give them to a TA, okay? And give it to TA. And yeah, so yeah, you are jumping ahead, but I guess we can do this. So please stand up. So this is Lin Yuche is our TA who will be handling most of the stuff. So the homework stuff, yeah, he is responsible for collecting and grading, and yeah, he will also help grading some of the exams. Yeah, and also if you have a question, you can ask him. And yeah, I guess the homework is kind of okay now, but as long as you can give it to the TA in a reasonable time, it should be okay. And we have this nice policy where that if you really miss some homework, then one of the homework, the lowest grade, will keep it out as. So we'll select like, so when we calculate your homework grade, the lowest one will be kicked out, so you can miss one of the homework. Okay, and yeah, so contact, so the professor is me, and my office is in Taida 610, and this is my email, and this is TA, as you see, is in Che. And his office is at the next building, it's 资电馆444. And yeah, I put your email here, so the Gmail, yeah. And yeah, so if you have homework questions, you can go to the TA. And we use eLearn as our course website. Okay, and wait, I didn't update it here. Wait, actually, let me try. I should open this one. Sorry. Okay. And yeah, and also as you might have seen, we do like streaming a video. Although, so this is leftover from the COVID area because we were doing online course, but I found it's pretty useful for learning. So we keep the streaming here on my YouTube channel, but will not be responding to whatever question you have on the YouTube. So it's just a video there. Okay. And so if you want to ask question, you need to come in class. But if you just want to see the video, you can go there. And because it's streaming on YouTube, there will be paste broadcast. And also there will be technical issues sometimes. So I guess I reserve the right to fail a bit of a video. Like yesterday there was trouble with the school Wi-Fi, so sometimes the streaming failed. But hopefully it's okay today. Oh, okay, it's failed a little bit, so I should make this smaller. Excuse me. Let's see. Okay, now fitting. Yeah. And obviously this is totally English. And yeah, it will be fully in English. So any questions so far? This is the organization of the course. Yeah, if not, then let's go to actual teaching. Okay. We have a bit of time. Wait, what? Okay, this is weird. Yeah, anyway, so yeah, let's actually go to actual teaching. So this course is about quantum computation. So it's a combination of quantum and computation. Quantum stands for quantum mechanics. It's it's a physics concept, and as most of you don't know, but I will teach you. And there is computation, and yeah, this is what CS department people should know quite a bit. And so let's talk about quantum mechanics. So what is quantum mechanics, and why is it so different from classical mechanics? And I think it is most as a different way to view how information is stored in the universe. So it's a really fundamental change about how people think about information are stored. Because in classical mechanics, information is stored somewhere, and you can do measurement and do whatever thing, and you will learn the information. But quantum mechanics is quite different in how we think about information is stored in the universe. And there are two principles. So first is we think information can be all the information can be in superposition with each other. And the second one is that when there is information somewhere, it's in some quantum state, then you need to do measurement to get it out. Okay, and so this is the very high-level mental picture we have about quantum mechanics in this course. Okay, so we think there are some quantum stuff. So there is some quantum part of the world is in this weird quantum state. And as we say, we need to do measurement, and we'll do measurement to get the information out of it. And we kind of think that ourselves as observers classical thing. So because we think classically and we store data classically. Okay. And yeah, so this is an easy picture of thinking about quantum mechanics. So there is a quantum part and there is classical part. When you want to get classical information out of a quantum system, you need to do this measurement. And then we can digress a little bit here. So if you say this picture to physicists, will be a lot of them will be angry because this is a little weird to physicists because we think quantum mechanics as a fundamental theory to the whole universe. So actually we think, so most of the physicists, they think that quantum system should be everywhere. Like this line here we are cutting between quantum system and classical system is really artificial and it's not well defined. So actually some people think that everything should be quantum. Right? Everything should be quantum. And but if you think that way, then there will be a lot of philosophical issues. And we don't want to talk about the philosophical issue here. So here we have this simplified picture, thinking that there is some quantum part, there is a classical part, and usually in practice it's pretty obvious that which part of the system is quantum, which part of the system is classical, because most of the system is classical, you need to work hard to keep yours in quantum. And yeah, so this picture works pretty well in practice, and this is what we're thinking about. Okay. And so we're kind of in a different order. So this is about measurement, and there is a superposition. We will see this in more mathematical detail. And for now, we think quantum state can be any superposition of classical state. So what do we mean by superposition is linear combination. So for example, okay, so now we are going into a little computer science. So a classical bit, we know it has two states. Okay, so this is what we mean by state. It's like the position or the state the system can be in. So a classical bit can be in 0 or 1, right? And then a quantum bit, so a qubit, it will be a superposition of the 0 and 1. And what we mean by superposition is that it's a vector. Okay, so we write this, we'll see this notation more. But we think 0 as a basis vector and 1 as a basis vector. And your quantum state will be a linear combination of these bases. So it's a vector in a two-dimensional space with this coefficient A and B. And A and B is going to be complex numbers, and they are going to be called amplitudes. Okay. And there are reasons why physicists think about universe is iterating this way. It's mostly because, well, linearity is nice. And when they solve like wave equation, etc., everything is in superposition. Okay. And okay, so back to measurement. As we said, measurement is how you extract classical information out of a quantum system. And okay, so we actually only talk about half of what the measurement do here. Okay, so measurement is what you do to extract the information out of a system. And well, in classical world, you also do that, right? You can measure your height, and you will know your height. You can measure your weight, you will know your weight. But in quantum mechanics, the different thing is that when you do measurement, you also change the quantum system. Okay, so the quantum system will collapse into the classical state with probability equal to amplitude squared. So for example, if you have this weird quantum state, the superposition of 0 and 1, A0 plus B1, and when you do measurement, then then your state will be changed into either 0 or 1 with random probability. Okay, and the probability is with this A absolute value square, your state will become 0, and with B absolute square, your state will become 1. And then your observer will learn this classical information about whether it becomes 0 or 1. Okay. So this is what happens in measurement. So, so you learn, well, you will learn some classical information out of it. And so here you learn one bit of information of whether your system becomes 0 or 1. And you also change your system, you collapse the system into the 0 or the 1. So what this means is that when you measure the system again, so say your system collapses to 0, then you measure it again because it already becomes 0, then you will always get 0. Okay. We'll talk about this in more detail later. And then there are interesting questions you can ask. So you think this superposition, you have like A squared probability to become 0, B squared probability to become 1. Then isn't this just like flipping a coin? So is superposition just, you can just describe this as a classical random variable, say, because if you measure the 0 and the 1, then it's really just like flipping a coin with probability A squared and tail probability A squared and head probability B squared. So maybe everything is just a classical random variable. And also you might hear that the superposition allows exponential parallel computation because there is exponential large space in this number of qubits. Okay. And this question will have the answer with the later part of the course. Okay. Okay. And I guess as a spoiler, So the quadrant here is no. That's why quantum computation is better than just classical computation with random variable. And here the answer is also no. It's mostly, well, in most of the cases, no. You don't get exponential parallel computation all the time. You will get exponential speed up only if you design your algorithm carefully on a suitable question. Okay, problem. Okay, any questions so far? So that's the very high level introduction about quantum computation. Okay, so those are easy things. So let's go to harder thing. Okay, now we need to do actual work now. We start with teaching you not quantum mechanics. We start with teaching you math. Okay, so this is I'm not sure this is a review anymore. I saw that you learn all of this in linear algebra. Then when I teach linear algebra this year, I realized you don't learn linear. Some of you don't learn linear algebra in complex number. So hopefully this is a review for you. If not, and hopefully you can learn this really quick. And anyway, so the mathematical foundation of quantum computation or quantum mechanics is linear algebra. So we want to know we are dealing with vectors and matrices, inner product, etc. Okay, and but we are using different notation for linear algebra, and we will use this bracket notation. Okay, bracket notation. And it's called bracket because when you write this thing, it's a bracket. Okay, so we will see an expression like this thing. Right? This phi bra, we'll write something like this. Phi and some a and psi this thing, and some something about Greek letters. So okay. So this thing is called phi, and this thing is called psi. They look very similar, they're pronounced very similar, but it's a little different. So if we open up here, it's called psi. Okay. And anyway, we say it's linear algebra, so this thing is actually just multiplying some row vector with a matrix with a column vector. Okay. So the most basic thing in quantum mechanics are those Kate vectors. Okay. So you write in this K notation, so something straight and like a triangles in here. Okay, so this is called the psi Kate. Okay? And when we write a Kate, it just means it's a column vector. For example, you can have your psi Kate as just this 1 and 2. Okay, so it's a two-dimensional vector with two elements 1 and 2. And also we are in complex space, so all the number here can be complex number. Okay. And then we use these capital letters to represent our matrices. And for physics reasons, sometimes those matrices are also called operators. Anyway, so the capital letters are usually matrices. And for example, we can have A equal to this 1, 2, 3, 4. So it's a 2 by 2 matrix. And then we have those bra vector. Okay. So you write as this. So this is bra of phi, and bra vectors are just row vectors. So maybe your phi is this row vector of 3, 4. And then we have this very easy notation here now. So we will write a bra vector with a matrix with a K vector, which just means we multiply them together with the matrix multiplication rule. So if those three things are like this, then your bra phi times A times K psi is kind of like an inner product, but with your matrix in between. And it's just this 3, 4 times 1, 2, 3, 4 times 1, 2, then you can do matrix multiplication. So this 1, 2, 3, 4 times 1, 2 give you this 5 and 11. And okay, because 1 times 1, so 1 plus 4, 2 plus 2 equal 4, so this is 5. And 3 plus 8 equal to 11. Then you have 3 4 times 1 in 5 11 is the inner product between those two vectors, and that's 59. Okay. So this is a kind of inner product. You will see a lot of those expressions, and there are outer product. Okay, and yeah, so outer product is you write a matrix. So you write a k vector, excuse me, before a bra vector. So that's a column vector times the row vector, and yeah, when you do the matrix multiplication rule, you find out that give you a matrix. Right, so if it's 2 dimension, it will be 2 by 2, and if it's 3 dimension, it will be 3 by 3. Okay. So those are matrix multiplications, and you can also multiply things by a scalar. So, well, it's linear algebra, right? So you can multiply any vector or any matrix by a scalar. So scalar usually written as a lowercase number. So example, you can have 5 multiplied by our ket psi up here. Okay, so it's 5 times your vector 1 2, and you just multiply every element by 5. So that's 5 10. Okay. And obviously you can also multiply your matrix and your row vector with some number. Okay. So any questions so far? Those are basic linear algebra elements. Okay, now let's talk about operations that are more interesting. And so there are 3 operations you can do on your matrix, and and they have different notation. So the first is the start operation, which is complex conjugation. So if you have put a star on your matrix, that means you do complex conjugation on all of its elements. So it's Bij means the ij's element of B. Okay, and there is a transpose. You probably learned in linear algebra course. So transpose, flip your matrix through diagonal. Oh, why is this so ugly? Okay, and so T should be up here. Okay. Yeah. Then okay, maybe I will do this. Yeah. Anyway, so when you transpose the matrix, then is ij's element becomes ji's element. Okay. So maybe I can go through the example here. So say your matrix is 1i to 1 minus I. Then when you do complex conjugation, as we say, you complex conjugate every element. So 1 become 1, and I become minus I because of complex conjugation, and 2 become 2, and 1 minus I become 1 plus I. So this is a star operation. And as we say, there is then the transpose operation. As we say, you swap through the diagonal. So you will swap the I with 2. So you have 1 2 I 1 minus I here instead, because the 1 2 element become the 2 1 element, etc. And then there is this special operation that we actually care most about is a dagger operation. Okay. So you see it's a little different. It's a dagger here instead of a T here. Okay. So a dagger operation, you basically do transpose and conjugate, complex conjugation together. And the ordering doesn't really matter. You can easily verify that. So you want to transpose your matrix and also do complex conjugation. So on the diagonal part, you just do complex conjugation. And on the off diagonal part, you want to do this diagonal swap, then do complex conjugation. So it's I gets swapped to here and it become minus I, and this 2 gets swapped up here and it become 2. And as we say on diagonal, you do complex conjugation, so 1 doesn't change, and 1 minus I become 1 plus I. Okay. And this dagger operation is pretty important because it's related to inner product complex vector space. Okay. Do we actually talk about that? Okay, maybe later. We'll talk about inner product later. But for now, you need to learn that. You can also do this dagger operation on vectors. So you can have a dagger of some ket psi, and you can also have the dagger applies on some bra phi. And that's just defined as you view this vector as a matrix. Okay, and and here is an important definition here. So if you apply the dagger operation on vector phi here, and it will become a, well, if you apply it on ket vector, so the column vector, it will become a row vector. And that row vector is defined as like I guess as a dual, if you call reading mathematical, as a dual of this column vector. But anyway, we'll just write that as the bra of this psi. Okay, so if there is a ket of some vector psi, some vector ket psi, and there will be some corresponding bra vector bra phi, and it's defined as this dagger on this ket psi. So I'll see an example here, and it's more interesting when you have complex value here. So this is some vector that we'll learn in more detail later. So this plus vector is defined as 1 over square root 2 and 1 and I. And as we said, then we do complex conjugation. So we do this, complex conjugation and transpose. So we do this dagger operator on it, and so you will flip this column vector become a row vector, and we also need to do complex conjugation. And so this 1 over square root 2 doesn't change, and 1 is still 1, but then you get a -1 here. Okay, so this is the plus state with the bra. Is the dagger apply onto this plus state. Okay, and we'll see that is useful when we define inner product. And then with those operations, we can define some property on matrices. And so property is, okay, so so a matrix is called Hermitian if only if it's equal to the dagger of itself. Okay, and yeah, so you can see that obviously it is only work for square matrix. Otherwise, the dimension of those two doesn't even the same. But anyway, so if a matrix is equal to its complex transpose, then it's called a Hermitian matrix. And here is an example of a Hermitian matrix. So 1, 2, and -I on the diagonal, on the off diagonal. So you see that when, yeah, you can check it easily. So the diagonal is real, so when you do dagger, it doesn't change. And off diagonal will get swapped, and when you do complex conjugation, you will get a -sign back. Okay, so this is Hermitian matrix. And another thing, so well, Hermitian was an adjective, now we have a noun here. Okay, so also there are matrices that are called projectors, okay, and usually is P for projector. So some matrix P is a projector if only if P squared equal to P. Okay. And okay, so this is a very general definition, and if you just go by this definition, there will be some weird projectors that are not Hermitian, not diagonalizable. But usually we only care about Hermitian projectors. And then if your projector is Hermitian, then they have very nice property. Because if it's Hermitian, as we will say later, if your matrix is Hermitian, then it's diagonalizable, and there you can think about its eigenvalues. Okay, and so you think about the eigenvalues of this Hermitian projector lambda i's, and then you plug in this equation, you will get that lambda I squared equal to lambda I. And that means that the eigenvalues of your Hermitian projector are either 0 or 1. Okay. So for example, we have a very funny projector here. So the projector is the identity matrix is 1 1 1 1 1 1 1. Okay. And obviously the eigenvalues are all 1, so it's a projector. Okay. And well, I guess we can check the definition first, right? So identity equals this, and obviously identity square equals identity, and so it's a projector. Okay. And then here we use the nice thing about our DIrac notation. But we can also write identity as the summation over this small projector on two basis elements. Okay. So we can write it as the kth of basis and the bra of basis. So for example, this one, the first one here will be is kth into the first dimension and the bra into first dimension, and this one will be the kth into second dimension and the bra into second dimension, etc. So we can write these off diagonal ones as this summation over I and all the basis elements. Okay. And let's check again that this is actually identity matrix. Okay. And so you apply identity matrix on some vector v, and then you will get the summation I, ei. This is your identity, and then you apply on your vector v. Okay. And and then you think about this thing, and so everything is linear, right? So you can pull this v into your summation I, and when you do excuse me, and now you have basically three matrix, although there's a column vector and a row vector and column vector. But you can think of that as three matrices multiplying together, and so you can resolve the multiplication in any order, right? Because there is an associative rule for matrix multiplication. So you can think about what it is ei times v first, and well, this ei row vector times your whatever v is basically just the you will just get all the, what should I say, the ith amplitude of your vector v, because maybe it's easier to draw this out. Okay. Yeah. So this is ei times v. So what is ei? Ei is a vector with a whole bunch of 0 and just 1 on somewhere and a 0, and so on ith coordinate is 1. And what's v? V is whatever vector. V is like a1, a2, to an if you are n dimension. So you think about what happens, you multiply those two things, then because there's a whole bunch of 0 here and just 1 here, and so this will just pick out the ai. So this is the ith element, right? Okay. So you see that this eiv will just pick out the ith coefficient of v, and so this whole thing is summation, and now this become number. So this is just ai, and and you still have your ei here. So ei, okay. And but this summation I, ai, ei, you think about what this thing, and this is just your vector v. So we spend a lot of time to say that identity apply on your vector v is your vector v. Okay. And hopefully this gets you more familiar with this bracket notation. Yeah. And also we can see this thing in some two-dimensional detail. Okay. So we think about two-dimensional. When you will have two-dimensional case, identity matrix is 1 0 0 1, and so what is kth of 1 and the kth bra of 1 is this 1 0 and 1 0, and as we say, this will correspond to this 1 here, and then this K2 will be 0, 1, 0, 1 because it has a 1 on the second dimension, and this will become this 1 here. Okay? Question about identity matrix. Okay, not, and yeah, and say a little more about projector. And usually when we use projector, we are using it as we think there is some subspace V associated with the projector. That's the space where your eigenvalues are 1. But let's talk about this in other way. Anyway, so we often say that if we have some subspace and we describe it as with some orthonormal basis Vi, then the projector onto V is kind of like this identity matrix. It will be the summation I Vi ket Vi bra. Yeah. So as you probably already seen here, each of those Vi ket Vi bra is a projector onto this vector V and Vi. And if sum over OI, then it's the projector onto this subspace V. And some schematic way to see this is that if you can write your space into this subspace V and some other subspace that's also going to be V, then your projector onto V should look like this. It will be identity on the V part and 0 otherwhere. Okay? So you see you have a whole bunch of eigenvalue 1 that correspond to this V part and the eigenvalue 0 to the orthogonal part. Okay. And yeah, so why is it called projector is because you apply this thing onto so if you apply this thing onto some vector a1, a2, n, then you will be projected onto the V part, right? So the vector also have a V and a V dagger part. And when you multiply those, then you will get A1, so that's on AV maybe. Yeah. And you will get 0 on the all other part. Okay? Okay? So that's why it's called a projector. Oh, we have 10 minutes. Any questions so far? Everyone happy with dagger and permission and the projector? Okay. Then people are good with linear algebra. Okay. Then more review. Then there is the inner product and the dagger operation. And as we say, the dagger is good for doing inner product because that's kind of how inner product defined for complex vectors. So for example, you have a 2k vector. So this psi and phi. And so psi we write out in basis element is summation ai. So a1 to an, and phi has coefficients b1 to bn. And so the inner product with those two complex vectors is summation. Okay, so now we have complex number, then inner product is a little more complicated than the real number inner product because it's not symmetric. So you will actually have summation ai start bi. So you have complex conjugation here. Okay. Okay. So it's important you have a star here. And we want to do this because we want the inner product with itself. Since the inner product with itself is always positive, that's why we need a star here. Okay. And now you see why we kind of want to define the bra operator as the dagger of ket operator, right? So now we see that if we use this bra of psi definition, then it's nice because the bra of psi is summation of ai start and the bra of I, but bra of I is just I, and bra of i's vector, And so if you write down this as a row vector, that should be a1 star, a2 star, an star. And you see that the summation I, ai star bi is just matrix multiplication of this vector and this vector, right? And so you see that you can write the inner product between psi and phi in this nice way. You just write as bra psi with ket phi. Okay. And yeah, so if you are really picky, you see that we are missing one line here, right? Because there's a line for the bra and a line for the ket, but I guess this is also something nice for notation that you can just skip the extra line here. Okay. So kind of glue the bra notation and the K notation together. This is something we'll do a lot of time. Yeah. So that should be not too confusing. But anyway, you see that we have a very nice way, very clean way to write the inner product. So that's something nice about bra K notation. And let's see an example. So if your psi is 1i and phi is 1 minus i, then the inner product between psi and phi is, so first you turn your psi into a bra vector. And as we say, you do transpose, so you become bra, but you also need to do complex conjugation, that's important. So I become minus I, and then you multiply those two vectors together. Multiply those two matrices together. So that's 1 and minus I squared equal to minus 1. This is annoying. Okay, so 1 and minus become plus, but I squared is minus 1, so it's a minus 1. And so 1 minus 1 is 0. Okay. And as we say, we kind of mentioned together before that the inner product between two complex vectors is not symmetric. So inner product of psi phi not equal to inner product of phi psi, but actually they are just complex conjugation with each other. It's pretty easy to verify, and actually we probably do this in homework. I forgot, but anyway. So this is actually, you can derive this from a more general result. Okay? So you have any matrix A and B, they can multiply together with each other, and you take the dagger of them. Okay? So you think about this whole matrix, and you took the dagger. Then that's a B dagger and A dagger. And this kind of come from the similar property from transpose. So if you remember from your linear algebra, so we also have AB transpose equal to B transpose times A transpose. And then you can just add the complex conjugation here. Yeah. And anyway, so from this factor, then you can derive this in a very algebraic way. Okay. So first you take, so you start with the left hand side. You have psi and phi and the complex conjugation of it. And but this is actually a scalar, right? Because, yeah, inner product is just a number. So it's actually a scalar, and so you can do a transpose on scalar and then nothing will happen. And so the psi phi star actually equal to psi phi dagger. Okay? Because you had the extra transpose and nothing happened. Okay? Now you have a psi phi dagger, then you can use the thing here because we think these are the matrix, these are the matrix. And that will be this phi ket dagger times this psi bra dagger, and as we say, the dagger you will just flip into, say, you will flip between ket and bra, so that become psi bra and phi ket, and we get this thing. Okay? Let's see, 2 minutes. Okay, and yeah, and as we say, we will use this kind of expression quite a lot, and so psi bra a phi ket is kind of our inner product. You can think of this as psi inner product with a applied onto phi. Okay, and or you can group them together in other way. then this will be the A dagger applied on phi inner product with psi. Okay. Because you take the dagger of those things, then you use this property again. So that's A dagger and dagger on phi bra, so that's just phi kate. Sorry, psi bra becomes psi kate. And yeah. And just like the thing we derived here, then you can have so this scalar, you take the star of it, and then the dagger of it, and then you just swap the order of everything, so that become the phi kate become phi bra, and A become A dagger, and psi bra become psi kate. And also the most important example, and also why we want to define this in this funny way, is that you take some vector and the inner product with itself, and that's the length of itself is square. Yeah. And I can probably talk about this a little more. Okay. And yeah, also the eigenvalue and eigenvector equation can be written in Dirac notation like this. So if A is something with eigenvalue is some matrix, and psi lambda is its eigenvector, then you will get this eigenvector as this psi lambda, and it's just multiplied with the eigenvalue lambda. Okay. And yeah, so we are exactly on time. So any question? Otherwise, we'll stop here and resume on Thursday. Okay. See you on Thursday.